So, we can write all these equations in the dimensionless form. Okay. So, you can write like for example, m, that is the mass, can be written as m dot by A lambda by Cp, that is one term. This is the dimensionless mass flux. You can normalize R by A. Okay. So, I mean these are the typical non-dimensional parameters. You define something called a Lewis number, which is basically nothing but the thermal diffusivity divided by the mass diffusivity, right. So, that is the Lewis number, and this is very important, especially in the case of combustion and other related things. So, if you do all these transformations, we can write the non-dimensional equations as rho v r square m by r square dyf by dr minus Lef minus 1 r square dyf by dr is equal to 0, m by r square dt by dr plus 1 by r square right. Okay. So, these are basically the dimensionless versions of the whole thing. So, temperature similarly can be normalized by T infinity and things like that. Okay, these are not important, but you can, so it is basically T is normalized by T infinity, rho is normalized by rho infinity. Okay, so that will take care of the things. Okay. So, at r equal to 1, that means non-dimensional r equal to 1. Okay, we could have written it as r bar also, does not really matter. The same boundary conditions now will translate to something like this. This is where the Lewis number comes in, as you can see, right, and dt by dr equal to mLv, T equal to Ts, where your Lv is basically Qv divided by Cp T infinity. Okay. Ctp infinity is basically nothing but H infinity. Okay. So, these are some of the basic quantities that we have written. Okay. Now, let us look at, so this actually shows that what happens at the interface in terms of the normalized quantities. Now, for pure evaporation, if you solve for Yf, it is basically 1 minus m by r. Okay. And T is equal to Ts minus Lv plus Lv, sorry, m is equal to ln 1 plus 1 minus Ts by Lv. Okay. So, that is the pure evaporation. In dimensional form, you can just work out the math because there is nothing more to do apart from algebra. Okay. In the dimensional form, your m dot will be given by 4 pi a lambda by Cp okay. So, here this particular factor, we define a factor called Bv or Bh, whatever you call it, Cp minus T infinity by T by Qv. This is called the Spalding heat transfer number. Got it. So, the mass flux is basically given by this into this, right, and this Bh is basically called the Spalding heat transfer number. Okay. So, m dot in that compact notation can be written as a lambda divided by Cp ln 1 plus BH. Okay. In some cases it will be written as BV, does not really matter, it is the same thing. Okay. So, basically what does this represent? The BH, the BH basically represents the impetus for heat transfer, in this case divided by the resistance to transfer. Okay. So, it is the impetus versus the resistance to transfer. Okay. In most of the cases BH will be greater than 0 and T infinity will be greater than TB, that is the surface temperature, right. That will be always be the case because it is a evaporation situation, right. Now, how do you go from the d square law from here? We have already established this expression, right. This is the using the Spalding heat transfer number. Now, how to calculate that, how the droplet will actually reduce in size? That is the most pertinent question that we have. Now, m dot is also given by 3/4 a cube rho L, which is basically given on the droplet size, right. Is not that so? It is given on the droplet size. Now, if you take dS square by dt, okay, that will be given by 2 lambda by Cp by rho L into ln 1 plus BH, right, because this m dot is the same as the m dot that we established here, right. So, what can be done is that you actually differentiate this, but retain the a square term, right, okay, and then you show that this is equivalent to that. Now, this is actually equal to minus kV, okay, whatever, that is just a constant that we have done over here. So, basically if we integrate this, this will become a square equal to a naught square minus kVt, right. This is nothing but the d square law, got it, okay, because it is a square given as the initial diameter reduces at a rate, okay, which is basically linear, right. So, you can also normalize this a square by a naught square to 1 minus kV a naught square into T, right. So, this will show a decay characteristic like this, right. It will start, so it will start with when a naught is the same as a 1, right. Okay. So, it will start, so the time axis will start from there, right, and you can see it is a gradual reduction of the slope, which is expected, right. So, because a decreases with time. So, this is basically the d square law that we have derived out of this entire exercise, right. So, d square, now there is another thing to this d square law, we have determined it based on the heat transfer, Spalding heat transfer number. There is also Spalding mass transfer number, which is nothing but at the surface, this is at the far field 1 minus the surface. Okay. So, this as you know is a function of the P saturation pressure, right, which in turn is a function of the T saturation pressure, right, because P saturation and T saturation are related to each other, right. So, the Spalding mass transfer number is given in terms of this. So, ideally Bm should be equal to Bh, okay. You can derive this d square law from either of the two situations, okay, and this should be equivalent to each other, okay. So, this is mass transfer. If they are not equivalent, the lower of the two basically actually governs the process, okay. So, this is either called mass transfer limited or heat transfer limited, okay. So, there are basically two things, okay, mass transfer limited or heat transfer limited. Okay. So, these are the two cases that you have over here. Okay. So, now that we have done all these situations, okay, now let us look at the first model is done, that is the d square law part is done. Okay. Now, let us look at the more the next phase of the models, right. So, because as I said d square law is limited, we already established from that presentation what the d square law entails, right. Now, under certain cases, of course, in normal cases, okay, what will happen is that your droplet you cannot actually neglect like this, you have to take into account the gradient inside the droplet. Okay. Now, normal cases what we wrote was simple, right, normal cases just now we wrote it. So, lambda a square or r square whatever you call it, right. Shiriniano uses capital R. So, you can stick to if you are reading Shiriniano's book anyway it does not really matter. So, one part is basically your m dot by 4 pi into the corresponding QV, Shiriniano writes it as L, that is the latent heat, it does not really matter either way, and we have already seen that the QL by 4 pi this is basically the heat conducted, okay, which in Matalon's notation we combine these two, okay, and said that this is QV effective, Shiriniano writes it as L effective, essentially means the same thing. Okay. These two are basically the same. Okay. So, you really do not need to bother about the notations, but whatever notation you use it consistently. Okay. Now, we already know that this particular term, and we did something to indicate that this is basically nothing but lambda L into r square into dt by dr coming from the liquid side, the liquid side of the interface. So, we can write it as Ls, okay, or you can write it as A minus, okay. Anyway, once again does not really matter. Okay. Now, normally if you cannot neglect this, okay, last time what we did was that we said that this is equivalent to dt by the time dependence of temperature, and then we said that we can be neglected if it is in the wet bulb limit, this can be neglected and all those things we said. But we are taking a case in which all these things cannot be neglected. Let us assume the more generic case like that. Okay. So, so in that particular case, if you look at this particular expression once again over here, okay. So, this shows that it is in the liquid side of the interface. We normally do not know what is this conducted heat flux value is going to be, what is its value, okay. It is nominally unknown. Okay. The droplet surface temperature, that means either TB or TS, okay. Once again it is a notation thing which is basically nothing but the surface temperature, okay, that is also unknown. Okay. So, someone needs to solve the heat diffusion equation within the droplet to know about all these answers, right. Otherwise, your surface temperature is unknown, your heat flux is unknown, your gradient is also unknown. So, there are many unknowns which you need to solve. Okay. Now, before we go this, we can establish a few things over here, okay, which will help us, a few quantities. Okay. Some of the quantities you already knew. Now, for unitary Lewis number, that is Le equal to 1, right. The Lewis number means your basically thermal diffusivity and your mass diffusivity are the same, they are of the same value, right. So, it is basically rho d equal to lambda by Cp. Okay. Now, m dot, if you recall the expression for m dot, okay, log of 1 plus b, right, that is what we wrote in the last one, right. Now, if your rho d is constant, which in normal cases it is, right, we already established this. So, I am just reiterating the same, this we already established, right, in just in the 2 slides back in the last lecture we established this particular thing, right, and we established the 2 mass transfer quantities, right. Okay. Now, based on this we can also define the Nusselt number, which is basically 2r dt by dr at S divided by T infinity minus Ts. Similarly, you can define something like called a Sherwood number. Okay. which is basically the mass transfer equivalent. So, YFS minus YF infinity dyf by dr at S. So, the Nusselt number is basically Nusselt number and Sherwood number is taken like that. Got it? These are definitions. This is no mathematics. Okay, we have just defined the what is the Sherwood number is going to be. Right? This will be useful quantities as we will see later. Okay. Now, if we do now only the liquid phase under liquid phase analysis, because that is something that we never did, and that is what we promised, right. The liquid phase analysis, this is basically to link the interface temperature to the liquid heating rate. Okay. How to link interface temperature to liquid heating rate. Okay. So, sorry. Okay. Okay. So, we have to somehow link the two. So, the boundary conditions and you can show this. Got it? That is also equal to log 1 plus B by B L is basically the latent heat. Got it? And the symmetry condition prevails at R equal to 0. That means your dt by dr, okay, at R equal to 0 is 0, right. You got it? So, that is the basic set of equations, okay. And the initial temperature of the droplet, you can say initial temperature was uniform and it was T equal to T naught, okay. So, the time derivative is considered in the liquid phase, but in the the time derivative is considered in the liquid phase, but not in the gas phase, and that is because the gas phase, as we already know, we have already established that the gas phase does not require, right. The gas phase does not require any such thing because it is fast, okay. So, I am sorry. So, made a mistake there. So, that is the equation, okay. So, that is this is basically a transient heat conduction equation. Okay. So, that we had done with that. So, that is the symmetry condition. Okay. So, how about estimating? So, you need to solve this equation. Okay. You need to basically solve this equation to get an idea of what will be the interface temperature and how it is linked with the liquid heating rate. Now, let us look at the question that I am going to pose over here is that we know what is the ratio of the important question to know is that what is the ratio of the liquid heating time to the overall lifetime of the droplet, because if the liquid heating time is very small, then we do not need to solve all this liquid phase equation, right. We are just concerned with whatever is the wet bulb, the temperature, right. Because the liquid is not getting heated anymore, it is just getting evaporated. So, whatever heat that is coming in is going towards evaporation, right. So, but in order to estimate that ratio, if we say that ratio is n, right, capital N, which is nothing but the ratio of liquid heating time okay, to droplet heating time. Right. So, there are two ratios, right, the droplet heating time and the liquid heating time, and there can be a very significant way of finding this. Okay. So, let us assume the liquid heating time is governed by tau h, right. So, what is tau h? Tau h is defined as the time required for a thermal wave which is originating at the droplet interface to move to the core, right. So, it is the time required for a thermal wave okay, to penetrate from droplet surface okay, to droplet center. Okay. So, tau h is therefore given as R naught square by okay. That is basically the diffusion scale, right. The time that it needs if it proceeds by diffusion, that is the time scale. You already know about all these things, right. So, the time that is required for the thermal wave basically to come from the surface all the way up to the center. So, that is some kind of a liquid heat up time, so to say. That means, when the droplet center actually feels that there is something going on at the surface. Okay. It is equivalent to saying like this, you are heating that wall okay, far away from me, I am sitting over here, I am not able to feel that there is something action is going on at the surface, right. I will only feel it when the temperature gradient will come and hit me, right. So, when I will feel that there is a rise in temperature, right. So, that we can call about that time lag, right, is basically called the effect actually penetrates and comes all the way up to me. So, this is something like a so from a droplet perspective, that is something like the droplet heat up time. Okay. Now, the droplet lifetime on the other hand, lifetime is given by tau L. What is the order of this? Its order is 1 minus R naught square, okay, dr square by dt minus 1. So, tau L is basically given as rho L R naught square divided by 2 rho d log 1 plus b, right. Okay. So, if we take the ratio tau h by tau L, which is given as n, is basically given by 2 lambda CL by Cp log 1 plus b. Okay. So, that is something that can be computed, right. So, that is the computation. In most of the cases you will find that tau L and tau h are of same order, okay. This is particularly valid if the droplet has, if the large portion, if for a large portion of the droplet lifetime, and it especially happens when your ambient temperature is high, particularly happens when your T infinity is quite high, okay, and you have higher hydrocarbon fuels, okay. Higher hydrocarbon fuels always show this kind of a characteristics where the droplet heat up time and the temperature are almost the same. Let us look at two graphs to illustrate this particular thing taken from Journal of Fluids Engineering. Okay. The temperature versus non-dimensional radial coordinate, right, and you can see even at 90% or 85% of the droplet lifetime, okay, still there is a slope. You can see that it just about reaches there. Okay. It has not reached here, this portion is largely shielded, is not that so, largely shielded, right, from the influence of what is happening there, right. So, you can see even at this is taken at 52% of the droplet lifetime, even at 85% of the droplet lifetime, still you retain a little bit, okay, where this has not really sensed, right. So, this actually shows that the droplet heating time, okay, is actually maybe a substantial portion, not always, but it can be a substantial portion of the overall lifetime of the drop, okay, and that is a very important concern over here, right, because our analysis and all those things depends on this. Okay. Now, if you look at the definition of BH, what it was H infinity minus HS divided by L effective, correct, something like that, where well you are familiar with Cp minus C infinity minus Cp into Ts divided by L effective, equivalent definitions, okay, it does not really matter. Okay. Now, here you can see that, okay, initially your L effective, okay, must be greater than L, right, because it is the initial heat up time. This happens during the initial stages, okay, when droplet heating is going on and evaporation is marginal, okay, droplet heat, because evaporation, as you know, is a function of the Psat, right, because as with temperature Psat goes up, so your evaporation rate also starts to climb. Okay. So, this BH, but initially this is large, but then subsequently what happens, it starts to decrease. Okay. Now, in that particular case, your BH, your value of the BH actually changes over the droplet lifetime. Okay. In fact, BH you will find it decreases by one order during droplet lifetime. Got it? Okay. It happens, it decreases actually by one order during the droplet lifetime. Okay. So, if you recall that what we did, if you recall this, that the type 2 model, okay, the type 2 model was basically where we considered that is infinite liquid conductivity, and type 3 model is this current one that we are actually doing, right. This is a spherically symmetric assumption, right. Now, type 3 model actually a type 2 and type 3 model are actually becomes the same, okay, if you assume that the lambda L is much greater than lambda, right. That means the liquid phase thermal conductivity is very high and B is small, okay, and Cl, okay, is much less than Cp. Okay. So, ambient temperature for of a few hundred degrees, that means when T infinity is of the order of 100 degrees, okay. This actually leads to the surface temperature Ts is the same as the volumetric mean temperature, volumetric average temperature of the liquid. That happens, okay, is always equal to the volumetric temperature of the liquid. In essence, it essentially means that the instantaneous droplet mass and the so the QL that we conjectured earlier is basically, therefore, if you recall this expression, right, when that happens, okay. So, the instantaneous droplet mass, and this is basically what we call the average temperature of the liquid, front. Okay. At one point of time, as we said earlier, the TL becomes equal to the T wet bulb, right, to the wet bulb temperature. When that particular thing happens, okay, this term basically boils down to 0. Got it? Okay. So, we have said that the so we have established over here, okay, that when do we actually require to solve for the temperature field within, we need to solve it for these cases, right, where there is a strong temperature gradient, as you can see, it is not negligible and it persists for quite a bit of a droplet lifetime. In that case, you have to solve this and you have to link it to the outer gas flow field via the interface conditions, right. Okay. So, that is very important. So, in the next class what we are going to do is that we are going to now consider what happens when there is convection inside. The convection part is very important. Okay. When there is convection inside, what happens to the analysis. Okay. So, see you next class.